Assalamu alaikum. We're gonna start the tutorial on VLSI Electric. This tutorial will be focused on designing a NAND with the two inputs in a layout level only. So to start with, we're gonna go for File, New Library, and then name our library. I'm gonna call it Tutorial 1, which is 2, no problem. Okay, then you go for Cell, New Cell. Here you can find you can create different types of cells: schematic, layout, icon. The schematic is the transistor level, the icon is the gate level, and the layout is the basically substrate level. So I'm gonna call it NAND with two inputs. You go to the components bar to see all the components you can use. Before explaining what are those components, we're gonna set some preferences. So you go to File, Preferences. You're gonna start here. So you click on the Technology tab. You choose Scale. This scale will allow you to change lambda, which is half the process. The specification given to us specified lambda to be 300 nanometers or 0.3 microns, which means that we're using a 0.6 micron process. Always make sure that your your technology type is NMOS. This is the one we are using. Just a side note, if you go to display grid, always make sure that the alignment of cursor to grid is size 4 1:1. This will this might give you a headache if it was anything else. So to start with, our basic components are an NMOS, a PMOS, a P-well, an N-well, a P-active, and an N-active. Moreover, you can have different polysilicons. You can have up to 2 polysilicon layers and like 6 metal layers. Of course, you can have other things like metal contacts, so that you can go from one metal layer to another. The basic starting point is metal 1 and polysilicon 1, so this is why you don't have a metal 1 like a contact for metal 1, which looks like the bluish line here. And this is the gate that we're gonna use to connect our contacts with the transistors themselves. So to start with, this is the design for a NAND 2. A NAND 2 is basically 2 PMOS transistors connected in parallel and 2 NMOS transistors connected in series. We're gonna connect them to a VDD rail and a ground rail. We're gonna have also a contact, B contact, and the output, which is A NAND B. This code is for later. Okay, so to start with, first thing to do is to place the NMOS and the PMOS. Okay, so now it's always a good thing to remember that we need to label those, and it will be useful in creating the SPICE code for future simulations. So you just press the block, go to Tools, Simulation SPICE, and Set SPICE Model. What will this do is it will create a SPICE name. Yeah, for zooming you just press Ctrl and the mouse wheel. If you can now, since the SPICE model name is actually below the block itself, you cannot just simply click it. You need to hold the Control button and left click it twice until the X is appearing on the name. Then you need to press Ctrl I to open the properties menu. This is PMOS. Okay, this is capital. Size is 3 and the rotation is 90 degrees, as you can see. We do the same thing for the NMOS. Press it, Tools, SPICE Simulation, SPICE Model Name, Control double click, Control I, NMOS, 3 and 90 degrees. Okay, now we start with the actual design of each transistor. The PMOS requires P active and the NMOS requires N active. This is trivial for now. And yeah, so what we need to do is start scaling our transistors. If you double click a transistor, you can see that we have the width, the length, and the rotation. Our specified width is 12, and we're gonna rotate it by 90 degrees. You can leave the length, it's default. And these are the positions for placing them within the grid, so it's fine. Next, we need to scale the actives with the same scale, with the same multiplier. So it's going to be 12 and 12. Instead of going into each block and changing it alone, you can simply press Shift, click on the blocks, then double click one of them, and you'll get a window with the multiple blocks. Then you can change the size, do whatever you want. I think I'm gonna just rotate them by 90 degrees, both of them. Same thing goes for the NMOS. This is 12. This is 90. Oh, sorry. Let me just mark those so that we're done with them. This is 12, and this is 90. Cool. Now, I know you're thinking, why isn't the PMOS double the NMOS? Well, this is because we're trying to get equal rise and fall, and for a NAND 2 gate, the PMOS and the NMOS have the same size. This is just for the NAND 2. And okay, now what we need to do is connect the transistor itself with its actives. So you go to the transistor, you left click it, you will see this small white bar, right click that thing and go until it's locked in onto the P active. Same thing goes for the other P active, and we'll do it. Oh, sorry. See, now here it starting from the right. I don't want to do this. I want to start from the left, so I click it and then I go here. Okay. A very major concern that you always need to trouble yourself with is the connection wires, or it's basically called arcs in here. You need to double click it, go to press more, end extract and extension, and neither end. If you look at it, when I press OK, it shrinks from both ends, and when I move this guy, it's fine. However, if we go to the other one and we just move it, okay, it's not changing. So you're gonna see it when you do it. It's gonna be really irritating, and you need to do this always for every arc. Okay. If I zoom in a bit, there's another rule that we need to apply, and this rule is simply that the spacing between the active and the transistor is 3.5. As you can see, there is a small text coming out. When I move the active itself, it says 4.5, and now it's 3.5. You just need to look closely. Same thing goes for the other side, which is 3.5. Okay, I'm going to do the same thing for this one. This is 3.5. Okay, sorry, replace this one here. What's next is that we need to press this guy, the PMOS transistor. Instead of creating another one, I will do a duplicate, which is Control M, or edit duplicate, and I will place the other PMOS here next to it. Same thing goes for the NMOS. So Control M and place. It will place it along with its labeling and the specified width that we already did. This will save you a lot of time. We'll need another P active, so Control M and place. Okay, so I will connect this one here and this one. Oh, sorry, yeah. If you start by connecting the P active to the NMOS, it will start big. So you don't want to do this. You want to just do it from the PMOS side from the transistor side to the active. It's a simple rule that you always need to follow. End extension, neither end. Don't forget to do this for all of them. And the spacing is 3.5. If you go more, it will give you an error, so just be careful. Let me see. Yeah, this is 3.5 and okay, cool. Okay, now for the, since we have parallel in the pull up and series in the pull down, for the PMOS we need an active in between the two transistors. However, in the NMOS, since they are in series, you don't need a P active, so they'll be connected to each other. You're gonna see it later on. But so this one will be connected to this one, and this one will be connected to this one. Okay, you can move them with your arrow keys as well. Okay, and then neither and extension. I just chose them both. Oh yeah, when you approach a transistor with another transistor, it will give you an error always, so just ignore it for now. If you just release it and re-grab it, it will hold it again smoothly, so it's fine. Okay, after doing so, every once in a while just press F5. As you can see, it will give you a quick review. It's like a somewhat of a compiling. It'll show you any errors or warnings. Let's say I want to make this like too close, and it'll give me error, and I know I'll find an error, and then I'll press F5. Okay, why? So we just leave it for now. Okay. This program's crazy. Okay. But it is also too smart. Yeah. So okay. Now we have our PMOS transistors and NMOS transistors ready. You just get the NMOS close to the PMOS so that the outer edges are almost interconnecting with the outer edges of the PMOS. Basically, this is your substrate, so you want to make them on the same thing. And the next thing that we need is the N well and the P well. This is an N well and this is a P well. So an N well is simply a negatively doped, not negatively, it's doped with N element, that is, it's highly doped with an N element, so it will have much more carriers than the actives. Same thing goes for the P well, which is the highly doped with P elements. Now N is negatively charged, so it's going to be connected to the VDD, so it will draw current in a good way, and P is connected positively, is a positive thing connected to ground. You need to scale them. In our case, the rails are simply double the size of the transistor, so it's going to be 24 and 24. And always make sure that the outer edges are almost connected or interconnected with the outer edges of the transistors. Okay, so this is our VDD and this is our ground. You double click it, you get the properties, change the name to GND, and of course you'll need to change the font so that it's a bit more visible. Okay, why is it like this? Just leave it. Same thing goes for VDD. Okay. Okay. Now what we need to do is connect the transistors to the rails. You go to the outermost right P active, left click it so that it's highlighted, and then right click it to start the wire and connect it to the N-well. You'll see a blue connection wire. This is a metal 1 layer arc connector or a wire connector. You go to the leftmost P active and connect it to the VDD in the same way. Simply this is a parallel connection, so both transistors should be connected to VDD as it's shown over here. So this is with different scales, but this transistor is connected to VDD and this one's connected to VDD. Same thing goes for the NMOS transistors, but in this case we only need one to be connected to VDD and the other one should be, oh sorry, this is because VDD is highlighted. I need to highlight this P inactive and then start a wire and run it through. Okay, this is a bit crazy, so come on. Okay, how about if I go from here? Okay. Just leave it for now. Okay, so let's try it again. Take this. Let's try to compile it. Oh, we have some errors. To propagate through your errors, just press Shift and the dot or comma. It'll show you where are the errors. Oh, okay. The spacing. Let's see. Oh, I think it's because this area is overlapping too much. Let's pull it down a bit. Try it now. Yeah, it's fine. 0 errors and 0 warnings. Okay. For this kind of connection only, you don't need to do the neither end thingy. And now you need to interconnect the gates together. So you just highlight the PMOS and right click it and go towards the NMOS. Same thing goes for the other PMOS and NMOS. Now, as you can see, the P actives are normally connected using wires. However, the transistors are connected using the polysilicon. The next step is that we need to put the gates and another gate. You highlight the polysilicon, you connect it to the gate. Same thing goes for the other gate. And I think we're almost done. Yes, so need to place this one here and connect it. Okay, so let me tell you what I'm doing. I will place another metal layer over the just around here for a while, and then connect it with this arc. Now it's connected. Let's press F5, 0 warnings. Same thing goes for each gate. Okay, it's fine and fine. The last steps is naming our nodes. So you just highlight the gate, go to export, create export, and this will be our B input. Control E, this will be our A input, and sorry, just a second. This will be the A NAND B. Cool. Design wise, we're done. We just need to add some small code. This code will be used in the SPICE simulator. Let me do F5. It's fine. There are two other types of tests that you need to go through. It's there in tools. ERC is the well check test. We have two errors. What are they? Not connected to ground, VDD, and P well. Okay, so let me press F5 again. Go to tools, ERC, check wells. We have two. Oh, I think I know why. Just delete the naming that we have done and highlight this, press Ctrl E. We need to export the name, not just name it. Ctrl E, this is our G and D. And if you want, you can just change the sizes. Make them 3 for now. Run the test again, and it's fine. No well errors found, so this is good. Your design is fine. Okay, so we passed all the tests. The last thing we need to do is add a strip of code. Okay, this is bad. I think I need to save it maybe. Save library as. And let me see this again. Okay, so no save type. Let me try to open a new library. Call it tutorial 1. This is the problem with Electric. It's a bit buggy. New cell. Again, NAND 2. So simply copy the whole thing to this layout. Okay. Let me delete this one. Close this library and don't save it. And simply save this one. It's tutorial 1. I just need to rename my contacts. This is my B. This is my Control E A. This is my A NAND B. This is my VDD, and this is GND. Okay, passed the F5 test. ERC test is also passed, so it's fine for now. You go to MISC, spice code, you see this, just place it anywhere, Control I, multi-line, and start typing the exact same text. It's a spice code, so you don't need to invent anything new. Start by setting VDD to a 5 DC. My V input will be A, which is simply a 0, starts with a 0, and then it has a pulse with an amplitude of 1, a low time duration of 10 nanoseconds, a rise time of 0.5 nanoseconds, a fall time of 0.5 nanoseconds, and a low time of 20 nanoseconds. You will see this later on. My V input 2 is B. It will be simply DC. And I will add a, okay, you don't need to add a load, just say you want the transient. Yeah, just add the load, it's fine. The output load is from 0 to 500, for example, femtofarad. You can change it to whatever you want, it's fine. We want to see the transient response from 0 to 40 nanoseconds. The last thing you need to do is to include the, it's dot without a space, and then include C where you saved the C5 model, the one I sent you an email telling you how to download. So I think it's gonna be in electric and C5 models. I think this is case sensitive, so you need to make sure you copy it exactly. Change the size, no rotation here. Then this is just for placements. I will change the size of those so that they're visible. Control I. Okay. Okay, so it is in my C directory. And yeah, oh sorry, I have this by mistake, I think. Yes. Just be careful when you're typing this text, it's a bit messy. Yeah, you need to download LTSpice and link it. This is also mentioned in the email. I think it was tools, spice CDL, and here's the path for my LTSpice, and this is a code you need to write it. Set spice 3 and spice level 3. Press OK. Tools. Write spice deck. Let's hope. Yep. Okay. Couldn't run. Blah blah blah. Okay. Don't care for now. Let's try it. Run. Okay. Okay. So to fix the error, just go to the spice code that we just wrote. Add 5 C5 model. And change our output to a NAND underscore B, the label that we had for our output. And okay, let's run tools, simulation, write spice deck. Okay, right click, add trace, choose A, B, and A NAND B and B. So okay, the green line is our A input. As you can see, we have approximately 20 nanoseconds of rise time and 0.5 nanoseconds high time and low time, rise time and fall time, 20 nanoseconds of high time. So this is the response of our gate. Just get a screenshot and that's it. For the, if you want to design a NOR gate, it'll just be the almost the inverse of this. So you'll need two NMOS in parallel and two PMOS in series. Just flip the orientation, just redesign it and it'll be fine. And that's it. Thank you. Don't forget to subscribe, share, and